Okay, let's start. Okay, so welcome everybody to the AMOROSO workshop, the first two. But this one will be more of a hands-on practical course on ROS computer vision and SLAM. We'll be doing it in English. I hope that's okay for everybody. If not, then please let me know. Then we have an issue. But all right, so that's great. I'm gonna walk you through our planning quickly, and I'll give the words to my colleague Tim, who will take over from there. So just really short, this is a Tetra project. It's a project that's basically subsidized by the Flemish government to stimulate growth and innovation, foster entrepreneurship, support clustering, stimulate business environments, encourage internationalization of business activities. So it's a 2-year project. We're nearing the end of the project. It will end in December. And like I said, this is the first of 2 workshops. We'll explain more about the second workshop later on today. So it's a technology transfer project. So it's applied research, and we're basically implementing some general use cases. And we're using those general use cases to develop a body of knowledge that we will then transfer to, the companies in the user group in the first place, and the wider Flemish region in the second place. Yeah, that's a bit what I wanted to say about that. So these are the goals of today. So it's basically to get started with robot prototyping using ROS and OpenCV, controlling a robot in a simulation environment using ROS and OpenCV, knowing the strengths and limitations of ROS, the robot operating system, explain the difficulties of robot prototyping, because there are a lot of them. Then that's basically the first part of the day. The second part is going to be about SLAM and sensors. Which sensors are available, which are useful, what are the currently available SLAM algorithms, what are their pros and cons, and deploying it in a simulation environment. And then in the end, we're also going to show a sort of full system where we show you how you can synthesize all the different components and put them together. Maybe a question to you guys, like, what is the, why are you here? Maybe, what is, if anybody wants to answer that question, like, what are you here to learn? Damn, put on the spot immediately. But is it about like learning more about ROS, or in general, or what is the goal of you guys?
Yeah, for me, it's to learn about ROS. So we make AGVs, but we don't use ROS for that. But yeah, we hear a lot about ROS. So
yeah, to see how you can maybe use implement it in your own system. Okay.
So can be useful.
Awesome. That's really good.
Perfect.
Perfect. And
SLAM, we can do basically.
Yeah.
What we can do with that, how easy or hard is it to implement it?
Yeah. Okay. But then that's all things we're going to cover. So no worries there. All right, let's go over the schedule. So, well, we're a little bit later, but yeah, that's because of all the traffic. No worries. We have some room to slide, hopefully. And otherwise we have to cut some parts short. So the morning program is we're going to dive right into ROS. What is it? Why is it? What can you use it for? Everything. And we'll have a lot of walkthrough examples, like hands-on examples that you can execute on the workstations we have provided. We provided workstations because from experience we know that if you have to set up an entire development environment, things will go wrong, and you'll spend half the day just setting up the development environment. So we provided ready-to-use environments for you guys. There will probably be a few more participants joining, so we would like you to pair up in teams of like 2 for the workstations. Otherwise, well, we don't have enough, basically. So that's the morning program for ROS, and then the second part is around computer vision. We'll not go into a very deep dive in computer vision because we don't have the time. We're mostly going to show you how it can be used in a robotics ROS context, basically how you can make them work together. And then the afternoon program is all about sensors and SLAM. There's a few breaks, of course, because otherwise we're not going to survive. And in the end, we'll have a short networking moment to finish off the workshop. You can find the workshop content on this link. So you can either type it into your browser or you can do it via your phone or whatever you need. Basically, all the slides are there. I'll also show you real quick what it looks like. It's a Google Drive, basically, with all the information. So I'll leave this on the left of the screen, maybe, and then quickly. Why is it? What is this? Okay, doesn't matter. In any case, we'll have these are the different folders of the different subjects we're going to tackle. There's also a learning path. It's mostly to follow along, like where we are and how you execute everything. We don't have an account. That's why it looks so weird. Okay. In any case, here you can also find out how to set everything up on your own device. And then it's basically step by step what we're going to do, how we're going to do it, some troubleshooting information, how you execute all the examples. That you can all find in the learning path. We also have a why? Where is my bar? You can also let me see, like this. Okay. We also have a resources document with all the basically background information. If you need more information, you can find it there. The planning document is there, and all the and all the slides are in here. Basically, we have a bunch of Docker environments that you will use to do all the hands-on stuff for the workshop. But you'll get a bit more explanation about that from Tim, who I think will be taking over from here. I'll open it.
Thanks.
So, okay, so basically the screen is slightly bigger than,
it is what it is.
Anyway, this way you can use Windows key arrow down to make it smaller. In that case.
Or just
all right.
present and
So go ahead. Take it away.
Still going to try. Will be good. All right. So an introduction to ROS. What it is. It's an open source framework to control robots. It's created to counter the rise of flexible robotics. So robot frameworks and robot components that you can interchange on a base. There's a completely open source mindset to it. It has a pretty large active community, and it has a lot of plumbing tools, stuff like that. So before ROS, and what you guys probably do, if you have a new type of hardware, you have to create a lot of own software or get it from manufacturer, and hopefully it can work together with the rest of the system, or you have to develop a lot of codes to integrate everything. So building device drivers, building communication system for a new robot, right perception, navigation, motion planning. Sometimes you can copy codes probably from previous project, but it isn't standardized. and that was a really big problem in the academic world. That's just before ROS, completely explanation from someone, just extra information. But the problem in the academic world at a lot of universities or research institutes from big companies like Honda and NASA, it's robotics projects, and most of the time they were just reinventing the wheel, just developing drivers, communication, stuff like that. Pretty irritating, and actually doing new work or new research. There's just a green part, it's just small part that was in the project. So they lost a lot of time. So with ROS, what's the goal of ROS? It's just stop reinventing the wheel. Start with an open source framework that's just a big massive passing framework, and just kill the red parts and just focus on creating new functionality and for us and doing new research. So just try to make the development much faster than before. So that's the goal. It's really good at it, to be honest. The website is ros.org, nothing fancy. The history of ROS. So it started with a research project at Stanford. So it's the AI Robotics group, and they had a really cool research project, and actually they built kind of a message passing framework, and the colleagues at the research center said, like, wow, this is very handy to use in other projects. Let's just open source it. So they did. Then they created Will Garage, which is was a very cool research laboratory and incubator. And after that, they started an open source robotics foundation. It's currently still active, and that's the main body that's controlling and guiding and releasing the open source ROS version. So they handle the steering committee and everything. So it's it's a decent body, open source foundation to steer ROS into the future. Some, in my opinion, irritating things in ROS is sometimes a jargon. So each several years there's a new release of ROS, but it's called distribution, which is very irritating because a lot of computer scientists and people in the technology world know distribution as just a type of Linux system, like Linux distributions, but the ROS community took that term and used it for a version. So if your distribution or ROS distribution is just a type of version of ROS. There are displayed a few versions, kinetic, melodic. Those are end of life, and currently it's noetic. It's still supported till 2025, and after that there's something called ROS2, but we'll get to that a bit later on. So it's used in robotics research, competitions, robots prototyping, everywhere where you want to do fast development of flexible robotics, actually. Now the cool stuff, technical stuff. So I already mentioned it's actually just a message passing framework. So it's a framework that can send messages, but it's a distributed framework. So you can create like programs. We'll see in a minute. They are called nodes, and you can compare it to the internet, which is also distributed. So it can run on different computers, and if some computers go down, the system still keeps on living, still is running. So it's a distributed system, interaction of nodes. And a cool thing is it's really robot and software and manufacturer independent, so and sensor independent. So the messages sent in a ROS system are standardized. So for example, we'll see some cameras and it's just an image message, but it doesn't matter which type of camera you use. The manufacturer, if it's ROS supported, will write the device driver and the interaction with ROS, and it will just generate a standardized image message. And if you want to take another camera on your robot, you just remove the camera, put another camera in it, start the new driver, and the rest of the system just keeps on working. So it's really independent of sensor type. It also has easy testing. We'll see a few simulators today. We're going to use, of course, simulator. It's also programming language independent. So standard support is for C++, Python, also Lisp, but I don't think anyone will use Lisp. So Python and C++ are the main ones. But you can write bindings in whatever language you want. So it's really programming language independent. And of course, a lot of code sharing. So distributed, I already mentioned it. So you can run it on multiple computers to gain the resources, or to add all the resources of all the computers to create a gigantic, strong system and a powerful system. So it can use just standard network interfacing. It's an interaction of nodes. So we're going to create a few programs today, which are called nodes, and they are going to communicate with each other in a graph. So that's what we're going to build today. And then you see, if you just kill one node, for example, if you have like a small robot system and it has a motion controller to control the wheels or the legs or whatever, and it just goes down, everything just keeps on working. You get sensor input, just keeps on working. The robot will just be stationary until the motion control is just rebooted or restarted. So it's benefits of ROS graph. So it's more complex view on a ROS graph. We'll get into what this all is in a minute. But it's just nodes communicating over a standardized way. So robot and sensor independent. So thanks to the standardized messages. For example, if you want to move a robot, there's a message called twist, which defines some movements. And if you send it to or Go robot or Turtlebot, so it's just the same message, and the translation is done in the background, and it just works. So it's really cool to just really quickly develop and move code from one type of robot to another type of robot, and it just keeps working. Also, simulating things is very important, of course, because you want to test in a virtual environment before you use it on a real robot and run into a wall or something. So Gazebo is a standard simulator in ROS, but we're going to see some other simulators today, for example, UNT and others. But the main one is Gazebo. It's not the most beautiful one, but decent, good one. Already mentioned, so language independent. Standard, there are three main libraries, C++, Python. Those are the most used. Of course, are also Lisp. A lot of other libraries you can create your own. So if you have a very cool programming language you use internally in your company, you can just write bindings to ROS and use the standard system that way. Also code sharing, apart from our institutions, we share code. A lot of big universities do that, and a lot of companies, for example, Bosch, use it for large agricultural machines, and they just share not all the things, but share some code. So that's pretty cool. Also, slide what ROS is not, because my students don't listen. So ROS is not an operating system, so computer operating system like Windows or Mac OS or Linux. ROS is really just a robot operating, so controlling a robot, robot operating system. It's not a programming language, it's just a message passing framework. So it's libraries and software, and you can program in certain language and control a robot thanks to ROS. Doesn't have a standard IDE or integrated development environment. You can use whatever editor you want. Today we're going to use Visual Studio Code, but if you want to use something else, we have internet access and you can install whatever you want. Also, ROS1 is not a hard real-time, doesn't have a hard real-time architecture. There are some libraries you can use in ROS1 to make it hard real-time, and ROS2 is better on that front.
Question.
Yes,
So
shoot.
do you still need a computer operating system then?
Yes, it runs on top of mostly Linux, or ROS1 does. ROS2 is more flexible on that front. You can run it on Windows, Linux, RDOS embedded. So the newer version of ROS is more flexible. The reason why we use ROS1 in this lecture will be explained later on. But you can install it on embedded devices. So a lot of not a lot, a few examples where you can use ROS. We started 10 years ago already with UAVs, with PixHawk and now PX4 UAVs, just controlling with ROS, just a base station, Linux base station, or a companion computer, a small Linux computer on top of the drone, and just make it autonomous and work for companies. PX4 is the biggest and, in our opinion, the best open source flexible system to control UAVs, and you're not bound to the party of China if you use DJI. It's a bit different. So it's completely open source. Same license as ROS. Maybe I should mention. ROS uses the BSD license, so Berkeley Software Distribution License, which means you can use ROS, change it, do whatever you want, and you don't have to share your code. A funny example, not really funny example, but a few years ago we were at a ROS conference in Spain, and was a military contractor there, and he was on stage explaining, yeah, we use ROS for our autonomous assault vehicles, but we don't. So thank you for your system, but we don't share code. So it's completely not okay, but accordingly to the license, it's fine. You can do that. So you can create commercial products and keep it closed source. It's no problem. So you will probably be booed off the stage like that person was. But all right. So why do I mention PX4? They even joined now for this year's ROS conference in New Orleans. So it's, if you ever want to do something with UAVs, use PX4. DJI also has support for ROS, but I have my concerns with DJI. Probably understand that. Another one is Cleopatra Robotics. These are just a few examples. It's way broader than this. Cleopatra Robotics has a few interesting AMRs. They also provide the ROS package for the Spot from Boston Dynamics. So Boston Dynamics has a Hercule robot, like you know, but they have their own SDK for C++ and Python. But Cleopatra Robotics incorporated it into ROS, so you can use ROS with the Spot. Unitary Robotics, so the Go 1 we have is from Unitary. They have ROS support for it. There are some downsides. Of course, there are a lot of other companies that use ROS, like Lockheed Martin, Boeing, BMW, Mercedes, Bosch. So a lot of companies use it, but it's not all good. A lot of downsides, and I really want to include a few of the downsides. It's important to know the benefits, but also the downsides. One downside is a slow adoption sometimes of technology. In the past, was the move from Python 2 to Python 3. I know in the complete computer science world, adoption of Python 3 was extremely slow, but here it was even worse. So in 2020, there was the first ROS release. That's the ROS we're going to use today. That completely supported Python 3. So it's the last ROS 1 version, supported until 2025. ROS 2 will be used after that, and that will also be used. I will also use Python 3. But yeah, the adoption of Python was an example. Another thing, we use an AR drone to teach drone programming to companies or to our students, and there was a very good simulator plugin and software for simulating the drone. First released by the university in München, and then some other university updated it, but it didn't work for Nuetic. So when I started to use Nuetic, yeah, we had to port it ourselves. So you're really, sometimes if you use, it's not really commercial UAV. It was just a toy, but it is really good to start learning how to control a UAV because it was cheap. If it crashed, it was €300, and you can control it with ROS. So it was for academic use and for teaching companies. The first UAV that was perfect, and so we had to port it ourselves. We did last year, I think was last year. Some porting, I don't know, last year, 2 years ago. And of course, we shared it. And on Reddit, for example, I created a post, and the reaction was, where were you 3 years ago when we needed this? So that's the downside. Sometimes you really need the support of open source enthusiasts to go to new versions. Of course, if you use software from a certain company, you can just ask the company, hey, there's a new ROS version, port it. But if it's like a toy, I mean, the manufacturer of that UAV is never going to create a ROS code, of course. So another thing, for example, slow progress to ROS software. The Clipper Robotics, they have a software for Spot. Again, it's for old versions of ROS, unfortunately. Luckily, there's a university that ported ROS to newer versions and even to ROS 2. So yet again, you need the support of the open source community to sometimes move forward, because Boston Dynamics doesn't support ROS out of the box. They have their own SDK. Also, our robot also doesn't support the latest version, but yeah, we fixed it, so it does now. All right. Another thing, it really depends on the manufacturer, is sports. For example, again, the problem that we have with our robot, the AMU data wasn't, it stopped working actually. And if you ask online, just don't get any answer. So we have to find it out ourselves. But that's when you rely on like the less supported and not so commercially good robots. So if you use Boston Dynamics, for example, which is more expensive, of course, yeah, then you do have software support. It's just programming. If you buy a knockoff Chinese brands, then yeah, let's be honest, then you're a bit on your own to fix things. All right, so what we're going to do today is use Nuetic. It's the latest ROS1 version. If you're going to start using ROS, you're definitely going to see a lot of ROS1 robots. The adoption of ROS2 is slow. It's good. I'll tell you in a few minutes what ROS2 is and how it improved on top of ROS1. But that's the focus of today's ROS1. Our robot is well, we made it support ROS1. So that's the reason we use ROS1 today. The development from Unity Robotics for their ROS software. It's an old version of ROS, but it's still active. Just a screenshot from yesterday, and you see still commits to a few weeks ago, and they included the new version of the robot, the Go 2, and it's also supported with ROS. So they are still active, but yeah, they have to update the version, in my opinion. All right. So ROS2. ROS1 has some issues, and it's almost 2025 will be end of life. So ROS1 was actually created for one robot, to operate one robot, but we see already a few years that if you create a robot solution, you have multiple robots. It's doable in ROS1 to just control a lot of robots. We do sometimes play around with multi-agent systems and swarm robotics with UAV, so it's possible to control multiple robots, but it's not ideal. So the open source robotics foundation just started from scratch to create a completely new version of ROS called ROS2, and specifically added the support for multiple robots. Also, it's usable on small embedded platforms, which is probably interesting for you guys. So we can just deploy it on really small CPUs. It's real time. Also, ROS1 expects a decent network, so TCP/IP network. With ROS2, it's not really necessary anymore. It can operate in non-ideal networks. It uses the DDS data distribution service as a network system. Also, ROS1 it was founded and created in an academic world. It's not their primary focus wasn't production. It's used in production, but it's if you work with it, you notice it's sometimes really academic software. But ROS2 is completely focused on production and industry. So yeah, that's benefit. Some technologies in ROS2. So they use zero-conf protocol buffers, queuing systems like ZeroMQ. But in my opinion, the best change is the data distribution service, which allows for really flaky networks to still be used in your robot system, still have a decent working robot system. They have, of course, yet again, a lot of distributions. The best you can use currently is AMOROSO bill, which is supported until 2027. And in the meantime, they have Iron, Irvani. Funny names. There's a reason why they use funny names and turtles. If you want, I can explain it later on, but that's not really important now. So, like I mentioned, the ROS2, it's a slow adoption to ROS2. For our robot, for example, we can control it with ROS2, but there isn't a simulation currently, unless we program it from scratch. That takes a lot of time. So we do everything with our robots currently in ROS1. Other solutions we do use ROS2, but for this we use ROS1. All right, so that's the brief overview, introduction to ROS. Any questions so far?
right. Now I'm going to jump to the next one. Yes. Right. So brief overview of the development environment. So in front of you, you have a workstation, but we're not going to use the Linux installation directly on it. We are going to use containers. What's a container and why do you want to use it? If you create something on your on a Linux computer and you want to move it to a robot or to another device or to a server if it's needed as a backend system for a robotics solution, well, you have to configure a lot of things, and sometimes it works on your computer, but doesn't work on the server, doesn't work on a companion computer of the robot. So yeah, you don't want to take your workstation and put it on the robot. So that's why we use containers. A container is a small software block that you can use and then very easily move between computers. So if you compare to virtual machines, I presume everyone knows what a virtual machine is. So you have your hardware computer. A virtual machine is just a piece of software that emulates a complete computer. So the CPU, the RAM, everything. And it runs on a hypervisor, so just on your computer, the CPUs since 2004 something support hypervisor and running virtual machines. The downside is you have to install a complete operating system in your virtual machine, and so that's called the guest operating system, and have all the libraries and binaries on top of it and test the boot. And you actually have just a virtual computer, which is not really handy to move between systems. More than a decade ago, Docker came out. Docker is the most used container system. What's a container? You have still your computer with some host operating system. In the case of Docker, it's Linux. So Docker is installed on your Linux system, and on top of Docker, you have containers. It shares some parts of the operating system, so the kernel is shared with the operating system on your computer, and that's it. So on top of Docker, you have a small, it's called container, small component, and just contains the binaries and libraries you need and your application. And if you want to start a container, it's just snap and it's just up and running. And it's very fast and it's very easy to move between computers and just runs. You don't have to boot because your guest operating system is already booted. It just directly connects to the kernel and just starts your container. And it's completely shielded from your operating system. So you can start playing around in your container and break it completely and just stop it, start a new container, and it's like nothing happens and everything is just back up and running again. So that's why we use containers. We deploy it on everything, on the companion computers of the robots, on our servers. We do everything in containers. It's not perfect. The biggest downside of it is sometimes it's a bit of hassle to connect hardware and patch it through to a container. But once it's working, it's really, really good. All right, so that's what we're going to use today. So already told you. So the container is just a standard piece of software on top of a guest operating system, and just you can compare it to a virtual machine, but just on steroids. Really, really hard, big steroids. All right. I also mentioned this already, I guess. So the benefits, it's small. It just, you don't have to boot. It's just, it starts instantly. So minimal overheads, and you have a standardized environment. So it's really good to create repeatable outcomes of your software, actually. So the biggest one in the world is Docker, the biggest implementation, best implementation of containers currently. So it has a lot of pros, some cons. So more tooling, you need to know what Docker is and other stuff. Sometimes also the performance, because you have a little bit of network latency. And yeah, of course, if you run multiple containers, they don't share the libraries. So sometimes storage-wise, it's a bit bigger. So if we go and look into a ROS architecture, but we're going to dive a bit deeper. Next slide. You have some nodes, some communication. So a graph of interactive nodes. That's a maybe it's like too soon, but that's a bigger system. So we have a lot of nodes communicating, and those can run on different computers, all in containers. So what we created was not multiple containers, but just one container. It's just an open source GitHub repository, and we call it ROS Noetic Docker. And you can just download it. It's already done on the workstation, but if you want to work it at your company, just clone it and you can build it. It runs just on a standard Linux system. You install Docker and just are in a few minutes up and running with ROS in one container. It contains the simulator, a few robots, and you can just start exploring and testing SLAM algorithms and computer vision and stuff like that. So that's what we are doing. So this is just one container, but what if you want to create a big environment? We also provided some bash scripts, so you don't have to memorize all Docker commands by yourself. So we have some explaining some bash commands. But if you want to run like 100 containers, you don't want to execute 100 times a bash script. Docker also covers that front. It has Docker Compose, which is just a text file. There you can define as many containers you want, and then you can run just a simple command and just spins up 100 containers. Then you can do your computer vision in one container. You're controlling a robot in one other container. Your SLAM in one container. Just divide it. You can also put it on different computers. For example, if you have computer vision algorithms that uses CUDA, NVIDIA CUDA, and you have a beefy NVIDIA card, you want to run it on a workstation, not on a companion computer of a robot. So you can you can set it all up and run it on different computers. I'm not going to dive into the syntax. If you want, you can ask for me later, but it's possible just easily to run some things on the robot itself and other things on a laptop, for example. In this example, it's a node. The robot has a camera and a node to get the data of the camera, image processing node, but it doesn't display anything. And if you want to, if it's running in production and there's an issue and you want to see inside the robot, you can just connect your laptop to the network and just start a ROS node for the visualization on your laptop and just immediately inspect the complete robot. So you don't have to be in the vicinity of the robot, just in a network and just run it. That's the power of ROS. It's just out of the box, just works. It's not really a hassle. If you Docker containers on multiple computers, there's Docker Swarm. It's the most lightweight way to team up a lot of computers and just essentially create a data center if you want to. So that's also, but I'm not going to dive into this. That's maybe a bit technical. So you can just run a lot of computers with nodes and spawn the containers on all the different computers and just accumulate the resources. to create a very powerful system or a more robust system. So on different computers. Yeah. And there are official Docker containers from the Open Source Robotics Foundation, but we are going to use the one we provided. And maybe we can start it. We can use it. So if you open a terminal in Linux, if you press the Windows key or the, I don't know which keyboards you have. If you have an Apple keyboard, it's just a command. Of course, I'm going to mirror my screen here. Just a second. Display, mirror, apply. I think that's better. It changes. Yes. So, all right. So if you press the commands key or the Windows key, you can start typing. And if you type TER for terminal, you get terminal on top. And then you can start just a terminal. Just press enter and you have a terminal. So let me zoom in a little bit. That's big enough, I guess. All right. I don't know if you all have a little bit of experience of Linux, but we'll go slow and easy. Every workstation is installed the same. So if you type ls, you see the data in the current directory. On this computer, there are a lot of video files, apparently. But we created a directory called repositories, and everything we need today is inside this directory. So if you type cd, which stands for change directory, and type repositories, you dive into the directory itself. Also, if you're not fond of terminals, which I understand, there's also a file explorer at the left-hand side in the dock. If you click it, you get a file explorer, and then you can also just click on repositories, and then you see. We have two directories called ROS noetic Docker, and for this afternoon, we have AMOROSO RTAP, which is a SLAM algorithm, for example. All right. But let's go into the terminal again. So if you are in repositories, you can type ls, and then you see the two directories. So let's dive into the ROS noetic Docker, which is the directory of our container. There's also a tab completion. If you wonder why I type so fast, it's just cd space capital R and just tab, and then it just auto-completes. If I type ls here, too big, then you see a lot of scripts we provided. So scripts end in .sh. We already executed a few scripts. So if you clone it at your work computer, you can just execute build images and then just start building all the Docker, the needed stuff. So the Docker image. And then we have some start scripts. We are going to start the Docker. So one is just starting the full desktop. If you have a webcam, but the workstation don't have a webcam, the standard webcam from Linux is passed through. And other start scripts for this afternoon. So let's start O3, I guess. So if you want to start a script, you type / and then I just typed 003 tab and just 003 start PXL noetic full desktop. And if you press enter, the container started. So much faster than starting a virtual machine. All right. Today we're going to use a lot of different terminals. So maybe it's good if I tell you how to start an extra terminal. You can right-click, I guess, here. No, I always use div. I'm going to just show you the keyboard shortcut. So if you press Control, Shift, and T, it starts an extra terminal, and then you have multiple tabs here. That's the most easy way. And if you keep on pressing T, you get a lot of terminals, of course. And you can close it with the X. So 2 terminals. Let me zoom in. All right. So we started in the first terminal, Docker container. If you want to access this Docker container from another terminal, like the second terminal, we also provided a script for that, and that's called attach bash to Noetic full desktop. So if I execute this one, /005, I'm already inside the same container. So we can start multiple consoles in the same container, same virtual machine. Right, so if you can do that, then we have a small base to do all the fun stuff later on. All right. So there's also one for a webcam, but we're not going to use it today. Extra bash processes. All right.
Just checking if I can. Just checking if I
All right. Questions so far? So let's dive into the concepts. All right, so ROS1, the framework, is built around works best on the Linux kernel. It's also mostly tested on Ubuntu. That's why we run the Ubuntu Linux. ROS2 is just a completely different beast and can run on embedded software, embedded devices and stuff like that. So if there's need for knowledge of ROS2, we can also organize a ROS2 workshop in the future if it's needed. So today, ROS1, we're going to create some nodes, and nodes are those processes in the graph to communicate. So each process will be a node. But before creating a node, there's something we have to start, and that's called a ROS core. That's a core process, which will be actually the manager of your system. So it's a process called ROS core. You can run it with just typing ROS core as a command. I'll show you in a few minutes. And after running that, you can start nodes, and they will register at the ROS core. And after they are registered, they can start communicating and start sending messages between other nodes. So ROS core is just the manager, actually. So in the first terminal, and I'll show you here. So this is my first terminal. I'm just going to type ROS core. So it starts, and you may execute it, of course, in your terminal. So it starts a server, and it displays a link. But if you click it, it won't work. It's not a web server. It uses similar protocols in the backend, but it's not a website you can go to. So it starts just a server on a certain port, but if you serve to it, you get an error response. So it's not meant to be used as a web server. but it's similar protocols. So, all right. So let's start nodes. So node is a basic component to process. It just communicates with other nodes. So a node, how will it communicate? It will communicate via topics, and just data streams. And a topic, you can publish data to it and receive or subscribe data from it if you subscribe to it. Other way to communicate between nodes or services, that's really just send a request and getting a reply after a certain amount of time. So let's try and start a simple demonstration node. It's just a simple demonstration included in ROS. So you start in the first terminal, the ROS core. So let's start a simulator in the second terminal. So I'm going to go to my second terminal. So first terminal is ROS core, second terminal. I'm going to type ROS run turtlesim underscore node. That will start a very simple simulator, just a 2D frame with a robot in it. So ROS run turtlesim node. Voila. I'm going to put it on top. So this was the command. Wow. And just a very simple example, just to demonstrate what nodes are and what a simulator is. All right. All right. So now we started our first node, and there's a command called ROS node list, which will print out all the nodes that are currently active in the system. Of course, we are going to use a lot of terminals. I also appended the terminal number each time on the box so you can follow. So we start at third terminal. Ctrl-Shift-T. Attach a bash process. So this is 5. And if I type ROS node list, you see there's a list of 2 nodes in the ROS system. ROS out is just for debugging information. So if you start logging information from sensors and from how the system operates, goes to ROS out. It's automatically started thanks to the ROS core. And then the second node is our turtlesim. It's just this simulator with our turtle. You can ask some information. So in the same terminal, you can just type ROS node info/turtlesim. So we're going to request some information about the turtlesim. So and it displays a lot of information. I'll show you just what it displays. So a node is just a process. So a node in the ROS graph. It can publish some information via topics. It subscribes or it listens to some topics, and it has some services. So what does it publish? It publishes, for example, a color, and it's between the square brackets. It's a type of message that will be used in the topic. So color sensor, you will receive a color message. It publishes to ROS out log information. So it will display or will put some log information. Also the post, it's some type of message. It listens to CMD underscore val for now to an unknown type. But that will change. And that's the way actually how ROS works on the front of publication subscribe subsystem. And between the square brackets is those standardized message types. Also some services, you can reset the turtle if it runs off. You can set a pen, so you can start drawing on the canvas, the background. It also has a process ID. So in Linux itself, it has a process ID, and there's some node which will communicate, the master node, which it communicates with. So it's just one node, not really fancy and not really working yet. So let's move on and inspect a little bit more. There's also the possibility to troubleshoot the network via ping operations. So you can just type ROS node ping and then the name of the node. And that will just, for debugging purposes. Of course, you're working in one container. If the network is flaky, that will shouldn't be. So just. All right. So a topic is just a data stream. It's a communication channel. It's a many-to-many communication way. So one topic name can be shared between a lot of nodes. A lot of nodes can just publish data onto such data stream, and a lot of other nodes can subscribe on the data stream. So it's the sender node publishes and the receiver node subscribes. And of course, it's the data on the topic has certain rates and heads for the system to update. But that's the main way to communicate between the nodes, just publishing data and receiving data between nodes. So there's a visual representation. For example, if you have a sensor like a camera and receive from the camera via the drivers the image, you can create in your sensor node an image type message in ROS and just publish it on the topic, and whatever node subscribes to the topic receives that image. So one or multiple nodes can receive that image. Just message passing. Another way to communicate is via services. That's a one-to-many way to communicate. It's a request reply. So it's more for things that are that take a lot of time. Like if you have a certain path planning algorithm that takes a bit of time, you can request and give the current position of the robot and the position you want to end up with as a service call, and then you wait for a reply to get the path back. So for path planning, stuff like that, it's better to use services. Or if you want to reset and spawn and clear, in this case, the turtle sim, those are the services that are active or present in this example. So this is a visual representation of a service. So path planner, for example, you can send a request in to the path planner that will calculate the path, and then it will respond. And just one-to-many, so many nodes can request, and you have just one server, one place that the service call will be processed by. All right. And if you combine it, you get a small ROS network graph for a small robot solution. So sensors that will just use topics just to publish the sensor information, an executive to combine it, for example, and that can send to path planner to start navigating. A visualization, because you sometimes want to see what's happening inside the robot, and motion planner to send data to move the robot. So that's how you split up all the things that need to be done in a robot system in multiple nodes. Just a small example, of course. And the benefit is, of course, if the motion controller goes down, the rest of the system keeps on working because it's a distributed system. the rest keeps working, the pet planning keeps working, the sensor keeps working, just the motion control that goes down. So restart it or fix it and your robot will move again. Or other way around, if the sensor goes down, the rest will work. And yeah, the robot doesn't see anymore. So you can build in a fail-safe system. If you don't receive any video feed anymore, it becomes stationary and notify the field engineer or whatever. Other benefit, if you want to switch this out, do another type of sensor, another camera, for example, you just have to change the code here and the rest will stay the same. Unless, of course, you go from a camera to a LiDAR, of course, then the executive will also need to change the incoming type to the correct data. So that's the benefit of this system. So if you look at the architecture, so we start a ROS master, it's the ROS core. So you can start ROS nodes that can communicate with each other. The ROS master, it's best to run it on the most stable system. Most time that will probably be the robot, if you have just one robot, or if you have like a large warehouse with a lot of AMRs, then of course, yeah, you run it on a server that's stable, and just a single node or just a few nodes on the robots that will send or register with the server. Benefit of ROS² it doesn't have a ROS master anymore. It's completely distributed, so you don't need a ROS master anymore with ROS². Another way. Benefit of ROS². So a computer on the robot itself, so a ROS master on the robot in this case, camera node, and the image processing node on the robot itself. Here, like I mentioned before, if there's something wrong and you want to look into the robot, just hook up a laptop on the same network and start up your visualization node, and you can dive into it and debug your robot. And this a bit more complex system where our students had to create a system to weed or pluck weeds. So we had a point of flora identification node that received data from a camera, and it was just sensor image. That's the standard image type from ROS. Also, the arm position in the camera was detected in different nodes. Of course, UR5 is just a robot's arm, and it was all combined in an executive node just to get a correct flow of operation and a mission planner. And it was on a propulsion system, so that's small tasks that our students had to make. Not going to dive in every message type that you see. I can use a few maybe. There are standard string, for example, or standard empty. If you just want to turn on or off a system, you can use an empty message, which is just full, just send it full. A string, yeah, you can incorporate some text. A point is just point in an image. X and Y coordinates and stuff like that. So those are just standardized messaging. That's the real strength of ROS. It's just a distributed system with standardized messages running on one or even multiple computers. Wow. All right. That's a complete system from a paper, which lets you see it can grow a bit bigger. And in the afternoon, we have the ROS graph of our robot, right?
Yeah. But I would hold on for a sec and show the URL to the Google Drive again.
Indeed, yeah.
It's easier to copy paste the different commands because not everybody has it open, I think.
Ah,
and
okay.
it's easier to copy paste commands
Yes,
because
yes,
I'm not sure everybody's already running the turtle sim
Correct.
appropriately. So maybe let's check if everybody's.
Sorry, it's always allowed to interrupt me if you can't follow or.
Yeah, I just noticed that's why I'm. I have to go. I'll be back in an hour or so. Hour and a half. Hour, I think an hour will be okay.
Ik denk dat die auto dichterbij staat.
I'll give you a few minutes just to go to the slides. Yes, of course, yeah. Let's take 15 minutes break.
Ja, nee, maar dit is gewoon content. Dat weten.
Helemaal aan het trappen.
Ik heb er heel veel van. Top. Normaal gezien 3 volt. Dan heb je die demo en dan heel veel.
Ja.
Dat is nou
Just change back. Sorry.
for this one, the ID LiDAR operation. This operation. I should have the driver installed for the wheel with the so you should be able to have that.
We also
We have that.
or with the sides.
Yeah, but it only goes to 12 meters.
Okay.
And then you can't.
Yeah.
But yeah, maybe you can. Yeah, you can switch. You don't have a measurement, and you have a measurement of the so, so I have that operational, or should have that operational to get the 12 volt feedback.
So
Yeah, I saw it. Nice.
Nice.
But I was wondering, you were using the real stance
Yeah.
435. Not the L5. Yeah, if you want to borrow it.
But it actually works because we.
Yeah, it works, yeah, but how quickly have you ever seen the resolution of this one?
No. It's much better.
It's much better. You can't even compare them. Because you have a lot of noise on that sensor. Look at this one. There's
still good.
yes, there was a time where they were discontinued.
We start working.
Yeah, they're still available apparently. Someone told me, I'm not quite sure.
Yeah, we have ours all a few years.
Yeah, I'm using ROS 2 now, but it's the same environment, so that's also a nice.
Yeah, we try also to use ROS every can. Fortunately or not, but
Yeah, but it shows that it's the same same environment. Actually.
Yeah.
Not much has changed. So this is basically just ceiling. So that's quite high res. You go to people, there's actually on to laptop here, there's actually very little noise. So you only have like a lot of noise on that screen.
Yeah.
But it's still doable, but it's mainly because you have your infrared which is being distorted by the screen and the light that's passing. But yeah, this is. I don't think you have this resolution when you're using the 435.
nope.
So, but I have that one. I should have that one working, and I think I'm going to keep it with that. I was wondering, do you have like internet cable with a connector? And yeah, maybe in the lab. No?
Yes, yeah.
Because I have that platform here.
Ah, okay.
And it has just a standard internet port. However, yeah, to demo it. Yeah, it's keyboard adjustable, but I don't have a longer cable at the moment. But yeah, it's mainly to show that it has a torque controller.
And you can keep 5 cables. Just send it to you.
Yeah, but I need to have the connector as well, because this is a special type of connector. This one.
Okay. No, we don't have.
Oh, okay, then I'll demo it just like.
Well, the standard LiDAR type cables we do have.
Yeah,
The,
but
what's it called again?
oh, it's okay. Yeah, but I'm quickly going to get the okay.
Pak je de fixed toolbox van Wout, die Wout zelf heeft gelegd bij onze toolbox.
Nee, Wout heeft goed maar ik kan erin kijken, maar ik denk dat hij
Ja,
zelf...
als Wout zelfs terug is, dan...
Of wagenplan. Ik heb een regelbaan op.
Ik heb wel een schroefdrijver hier gehad.
Ah, oké.
Waarschijnlijk niet.
Dat is geen hoor.
Ik heb mijn ladder.
Ja, dat kan wel.
Altijd.
Ik denk deze is waarschijnlijk veel te breed. Ja, ik vind ze wel. Ja, nee, daar moet je niet mee beginnen.
Ik denk dat er wel nog een andere schroefdrijver is, zo'n
En de ding is het.
Oh,
Ja.
fancy. Daar heeft hij dan mee.
Ah,
Ja, dat lukt niet. Dus dat is wat ik bedoel.
ik doe het nog met mijn hand.
Waar je from?
Italy.
Ja,
die past erbij. Ja, hier zijn gewoon een opzetstukjes.
Zo, is,
Het is geen woord.
you show how just torque.
Yes. This is a kilo wheel drive. Basically, it's a dual adjustable wheel, which allows you to have like a quick and dirty platform, which can easily rotate and
With suspension.
yeah, not real suspension. There is some maneuverability, mainly for taking dirt. But the main benefit is that it's velocity controlled, but also torque control. So basically, if it runs into a wall and it's torque controlled, yeah, okay, the wheels will stop, but your motors won't burn through, just because you have like skid detection. Yeah, it's not really a detection; it's a limitation on your power. So the amount of amps you send to your motors is controlled. So if you say, okay, I want the torque of a fixed amount, 4 newtons per meter or something like that. Calculates how many amps it needs and won't go higher than that. So if you put additional load on it, it will just stop. Or if it runs into a wall or a person, then it's kind of like a safety feature.
Like the Roomba against the wall.
Yeah, almost, yeah.
But then with the motor.
Yeah, so the Roomba has like
the
collision
switch,
detection
yeah.
and then basically just stops it. Because I also have a Roomba as well. At home, which I'm quite happy with actually. Platform.
But that motor is your product then? Or?
No, this is not our product. This is a product originating from research, basically.
Oh, okay.
So this has a payload of 175 kilograms. So basically, I can stand on it to be able to drive me anywhere. But this is on loan from our colleagues at Leuven. We have ordered one larger one, which will be able to load capacity of 275 kilograms. So the idea is that we can automate parts in a hospital environment of transporting food, medical supplies, and force over That's basically the idea. We did preliminary testing with this as a tower. So basically, you had a trailer on the back with cart. And because that's because that's how they do it right now. So I want to demo this torque control thing, but I still have to work a little bit on it. And also demoing some sensors. Yeah, just to show you how
a lot
easy it
of
is.
simulations for
This?
this.
We at our research facility we barely do simulation. We mostly work with real robots directly.
I'm done.
Yeah, okay, I started with simulation as well, but we do not go like into the deep high level or we're not trying to mimic the world one-on-one. We're trying to mimic to see if our algorithms actually work and then we directly deploy. It has its benefits, it has its downsides. Main benefit is that you directly see what the problems are. But in simulation, you can run several simulations parallel or something like that. Could be more beneficial. But we have the materials, so we love to experiment with real robots.
Way more fun.
Yeah.
No, because I use reinforcement learning, so I have to use a simulation.
Yeah, yeah.
Related environment. It's for the first. Reinforcement.
So you do a lot of parallel testing.
First space. Yeah, I'm working now with 5 years. Yeah. Now I also try to see how the values works. Then I have more
Yeah, you really have to document those rules.
Yeah, another one of my colleagues in the lab, maybe just like to start using the values that we have and have
They use specific libraries for
It's not always
sometimes all over, but I don't know what exactly. It's usually it can take a little fall, but when I started with this, it is pretty like first. I think it's
So you don't push it around like that.
No, we're not allowed. Where are you from?
But yeah.
Oh, you live?
Yeah, no, you can cross.
like,
That is nice. Working on that's
I heard that
U heeft ze gezegd, ja, maar is dat wel zo? Of je had gezegd, ja, dat zeg ik het af. Als het regionaal ziekenhuis in Disney, dat zal wel spreken van dingen met vrouwen, die
dat is altijd een keer.
Ze hebben het geprobeerd dit jaar, maar de eventjes gefaald. Dus ik heb het eigenlijk niet.
That's like development, just
Was handig.
you put this in there.
Maar ik denk dat dat wel bij lastig is.
So it's consultancy, so we have projects. So yeah, lately it's and yeah. Interesting. I don't know. When I in here for just 1 year. So
That was
and
the
I
purpose.
arrived at this realization about the life in Belgium. So and more of that. But it's something that is I want to know more about. So yes, here I don't see it.
Yeah, I know.
Yeah. But yeah, just to I don't know. What more is possible? Yeah, and I'm like going back socially. Nice, of course, but I mean, there's a lot of people I know that started working abroad and then went back to.
Last year,
Sorry again. All right. So small recap. So we started ROS core in our first terminal. We started the turtle simulator in second terminal, which is on top. And now we're going to start an extra node to control the turtle via a keyboard. So in a third terminal.
So each node needs an extra terminal.
Yeah, for now, yes.
So if you got many nodes, then you got many terminals. Well,
yeah, for this example, yes. So this will just start with by typing. But if you create a ROS system, you create just a specific file called ROS launch, and that will just start multiple nodes that you need, or other systems, or other ways to just start processes, and then you will start just automatically all nodes. Right? It's just a lot of that. That's for today, all in one container. So it's really making your hands dirty and time a lot, but it's a good introduction. All right, so let's go into the third terminal. That's maybe better. Voila. And let's just you can copy paste from the slides. Turtle sim, turtle, daily up. So ROS run turtle sim turtle underscore daily up underscore key in the third terminal. And when the focus is on the terminal, very important, then you can use the arrow keys just to I just pushed the up arrow, sorry, the arrow to the left, and we'll turn forward, turn. You can just move around with the arrows. All right, just doesn't look fancy, but underneath is just using the standard ROS principles and core components. So let's look into this now. Let's look into the graph. So a fourth terminal. Sorry, we're going to go to, I think, 6 or 7 terminals. That's just today. Normally you don't open that many terminals. All right, so on the terminal, execute 05 script to attach a fetch process to your container. Now you can run ROS run RQT graph, and I added an ampersand at the end. That will just start a process and just go into the background. So you can reuse the terminal. And here we have the graph. It's not really big currently, but we see we have the turtle sim, that's this one. We have the Tiliop turtle, that was the console, the terminal here, where you can move. And a topic between those two, namely turtle1 CMD file. That's just a topic. So the turtle sim is subscribed to the topic, and the turtle, the Tiliop turtle publishes to the topic. And I will just send messages, and we're going to dive into the messages. So let's first dive into ROS topics themselves. There's a command called ROS topic. If you type in ROS topic -h, you get help information. So each data stream, each topic, you can inspect. You can display the bandwidth. You can echo to see the messages on the screen. What we are going to do. You can search for topics. If you have hundreds and hundreds of topics, you can search for it. You can display the rate of a topic, extra information, list all the topics. So let's do that. You can even on the command line, and we're going to do that once, and then you're probably never going to do it again. But you can, from the terminal, use ROS topic commands to publish data to a topic. You're always going to just program in Python, C++ or something, but it's possible for quick debugging things. You can do that, but to be honest, I always just write up a fast Python script to test things and just use Python for debugging purposes. But it's possible, and we'll do it. So if you type ROS topic echo and then the name of the topic, I'm going to do it also in a terminal. So show you the command ROS topic echo turtle1 CMD file. And if you're going to move the robot, just going forward, you see there was something print in the terminal. So here just 2 values, 2 vertices actually, and going forward is on the linear, just going x for amount of 2. So if you keep pressing, you will keep seeing the output, the standard messages being just outputted on the console. So you can inspect. That's something we do use quite frequently. If something looks at a bit fishy, most of the time we just open a terminal and just echo the command to see if the data is coming through and everything is fine before opening other tools and debugging some more. So echo, we do use it a lot. If you go back to the visualization, let me go to the RQT graph, and if I press refresh, you'll see here an extra node which is subscribed to the topic. So now we have the turtle, the Tiliop turtle, so the keyboard control, and it publishes via the same topic, it's just the same name, to 2 other nodes. The turtle sim, of course, our turtle will move, and to the console to echo the message on the terminal. And this name is just a random, it's just ROS topic and a random string. That's just how ROS operates. Every node needs a unique name to be unique in the ROS network, ROS graph. So they just generate a random string and attach it to the name ROS topic if you execute ROS topic echo. All right. So if you list in a terminal all the topics, and I'll execute it and go back to the slides. So another terminal, number 5 already. Zoom in a bit. So if you type ROS topic list -v, -v is just for verbose, so it displays more information than just the standard list. The standard list just lists all the topics that are present. Verbose also displays the ones that publish and subscribed topics and the message types. So those are the topics that are published on. And you see here the CMD val has now currently new. It was unknown before. Now it's geometry messages twist. That's just a standard message in ROS to most of the time control a robot. Just twist meshes, which consists out of 2 vertices for linear and angular movements. All right. You can inspect it further. So if you execute ROS topic type and then the name of a topic, it will display the type. Very handy if you have a new sensor and it's ROS enabled and you start the ROS node of the sensor and you type ROS topic type and the name of the sensor topics, and you just always get the correct standardized messages that they will emit. And then if you want to see what's inside a message, you can also do that. For example, here we see there's a geometry messages twist, that's the type. And if you type ROS message show and then the name of the type, you'll get the information or the standard structure of that message. In this case, a twist message consists out of 2 vectors of the size of 3, 1 for linear, 1 for angular, and those are just float 64 values. So they always map to C types or G types. And that's how messages are structured. This is just a simple twist. There are messages for LiDAR, for images, all sort of things, and we'll show them later on today. We show the sensors, we'll show also the message types.
Yeah, message type and visualization.
Yeah, indeed, and everything. Then, and I'll going to type it in a few seconds. Don't really have to do this, but it's possible to publish on a command line. Just publish a message just by typing. You're never going to do that. I'm always creating some Python script and just use that. Then you have code completion and better syntax highlighting and stuff like that. But it's possible to use command line to publish, in this case, a twist message to a topic, and then the turtle will move. Normally I don't type it, but let's try it. So here's the robot. Maybe I go and turn it a little bit. So voila. So ROS topic pub -1 means just one message. I'm going to send it to the turtle 1 CMD val. That's the complete name of the topic. The type of message is a geometry twist. Then you have to supply 2 dashes just to start the data. And then let's go with, I'm going backwards, why not? Or just a random movement. We'll see what the effect will be. I'm just typing a few numbers No. Data no. Not really what this movement is. Let's see. It was spinning and drifting on its own. So yeah, so then you can just spin it around. It was 20. Okay, maybe I just 2. All right, that's better. 20 was better. But it's possible. But they're never going to do that. Actually, just write some Python code. I always say Python code because I don't know if you program in Python, but most of the times if you prototype something, you just start with Python. That's just the quickest way to develop something. And if you notice that something is slow or the performance need to be improved or memory management or something, then you just switched out that code to C++. And the cool thing is each node can be a different language. So you can have nodes that are written in C++, some are in Python, some in Lisp, some in Rust, some in Java, whatever. You can just combine all those things and just go, thanks to those topics with the standardized messages, doesn't matter which programming bindings you use in a node. You can just combine everything together. All right, so that's the messages. You can also send recurrent messages. The -r is recurrent. Maybe I can show you that also. Just send recurrent one message, and then let's see what's going to happen. And then the robot will keep on turning until you press Ctrl+C. Of course, there's no set axis on this system, so let's add something else. So I made a circle. Wait, beside a circle. It's protecting its nest or something. I don't know. Drifting. Yeah, that's also possible. All right, but just write it. Maybe I can keep on drifting and just go to RQT graph, refresh it, and then you see more nodes. Voila. So here's now an extra node with this the command on this terminal with this just a random string, and it's publishing via SIMD-val to ROS topic and turtlesum. So if I switch to the echo, which is this one, it keeps on outputting data. So the graph is growing. This is a very small graph, of course. If you have a real ROS system, you have a gigantic graph. And that's why you can here select nodes only and other stuff and refresh it and remove certain things. So, all right. Other things you can do is display the rate of the topic, just ROS topic, hertz. And you see the average rate, min max, stuff, standard deviation, stuff like that, just to inspect topics, debug information if there's something going wrong or you suspect certain nodes that are being flaky, just ping it, use a rate, stuff like that to debug. There's also some graph systems or program. It's called RQT plot, and yeah, I'm not going to start it. It can display the information in a graph, so you can follow visually. Most of the time, I just live in a command line and I just read text. But some, for example, is someone who loves visual things, so he uses RQT plot. All right, and then just some summary of all the terminology. A few terms will come in the next slides, but we saw a node. That's just a process to communicate in the graph. In the next part, we're going to make a package, which is a directory where we're going to create nodes inside. Publish, subscribe to publish and subscribe data. The master is the node that ROS core will start, so you can start standard nodes to communicate. It's just an overview. Questions? All right. So we saw the standard concepts. So let's go in and create our own code. And I'm going to stop everything. Control C. And if you type exit, you will stop the terminal. Control C, exit, exit. Let's clean everything a bit. Exit. That's good. I'll keep my ROS core running. All right. So we saw just how to start a node, but let's actually create a node. And before creating a node, we have to create a Catkin package. Catkin and Catkin package and Catkin workspace is the place you create your source code and your nodes. We already created a workspace for you guys. So if you are in your terminal and you type ls and you're inside your container, you type ls, you'll see here a directory called projects. Here we also have example code, so you don't have to code everything from hand, from scratch today. We have a lot of example code you can just copy. So let's first go into projects. And there are two subdirectories. One is AR drone WS. That's just a workspace if you want to play around with UAV, the AR drone. We're not going to do that today in the hands-on workshop, but if you want to, go ahead. We're going to dive into the Catkin workspace. So cd Catkin WS. And Catkin is the build system of ROS, ROS1. We type ls here. You see three subdirectories called build, devil, and source. Build and devil are just two directories that are needed to build the source code. But our projects or source code itself will live in SRC. So if we dive into SRC, there you see a few already existing packages. We already provided some packages that we're not really going to use today, like Pixel Drones Week. We have a drone week at PXL for international students to come and learn about drones. So that's already inside it. Sturm Foremost. That's a fun project. Looking at the alumni now. Fun project that our students have to do. And if they fail, they have to do the Summer for All project. Those are just projects for students. But I can show you later on. It's just a glass house or just a racetrack to race robots on and use computer vision OpenCV to make the robots autonomous. And also a LiDAR to avoid cinder blocks and cardboard boxes and stuff like that. But those are our packages, and we're going to create such package and put code in it and create a publisher and a subscriber and create a service and a client today. All right, so this is the place you want to be at. So Catkin Workspace is just a directory to create packages, ROS packages, in this case Catkin packages, because Catkin is the build system of ROS. So we already created for you this workspace. So it's on each workstation at the same place, but you can create it wherever you want. If you start out, look at the ROS documentation. So if you want to do that, but it's already done. If you want to do that, it's just a few commands, and then you have a ROS Catkin workspace, but that's already done. So a package itself, Catkin package. In theory, the most simple package ever is just a directory with two files. It won't do anything because it doesn't have any source code. But it's a directory. It's a CMake lists file. That's just a build system underneath. It's a C++ build system, and a package.xml. That's a package that will describe what the contents of your ROS package is. So this is the directory structure. So you have your workspace. Under workspace, you have src, and under the src directory, you have all your packages. Like here, we have src, and here we have own package. That's just the most simple package ever, but doesn't do anything. And then 4 packages, the YOLO example, which is for the computer vision part later on today. And then, of course, few packages that my students need to use. So those are this level. So let's create our own package inside this directory. So if you are in the src directory, you can create one new package. Let me do this. Voila. Too big. Voila. Smaller. It's a lot of typing today, but you're allowed to copy and paste. I'm stubborn, and I'm going to type everything. All right. So the command to create a package is called catkin create pkg package. Let's call it first package. You may call it something else, but first package. And then you have to add the dependencies. What we are going to do is add 2 standard dependencies from ROS itself. It's standard messages. Don't forget the S at the end. A lot of students, my standard courses, forget the S, and then it doesn't work. So standard underscore messages and ROS.py. We're going to play around with Python today. So those are the 2 dependencies. And if you press enter, so std messages and ROS.py. If you press enter, then it automatically creates the first package directory. It creates this package.xml, the CMake list file, and a source directory underneath it. And this directory where you want to put your source code eventually. This or yeah, this way. Right. So that's the command. Let's dive into the dependencies. So there's a command called ROS-pack or ROS package. And you can type depends1 and then the name of your package. And then it will display the dependencies of your package. You can type it for whichever package you want, because I almost took another package. So if you get an error, normally it's not the case, but if you install a lot of extra ROS software, it could be that there's an error and it will just say, hey, execute those 2 commands, and then the system is just reinitialized and everything works. But normally you get just output like here, like in this case, or here, ROS-pack depends1, and just the 2 dependencies you added to your first package. If you omit the 1, then it will display all the dependencies of your package, and that's a lot more. Right. Voila. So these are all the dependencies of your package. So a simple package like this also depends on Catkin, because it's a Catkin package, but a lot of other things, even generate Lisp for some reason. But those are all the dependencies, all the ROS things that are needed to have a working package. All right, so let's dive into the package itself. So if you go into the first package and you look at the package.xml, what's inside that? It's defined which build tool it depends on. In this case, Catkin. It's the only one we're going to use. And also ROS.py and standard messages for building and also for running. So it's just an XML file Most of the time, you don't need to edit it. Do we have still Vim installed on the system? Yes. Let me show you. Let's first go into first package and just open package. So what's also inside this file, it's the name of the package, of course, the version number, the short description, who maintains it. Currently, nobody. User had to do. And the license, very important. If you create a package that you have, you choose a decent license. And that's just some information on the package and some dependencies. But that's normally if you type the correct command, you don't have to edit it. All right. So that's the XML file. So the dependencies, you have first-hand dependencies. You can ask dependencies for each package in the ROS system. So the Python bindings is included in a package called ROS². And if you ask dependencies of ROS², you get the list. But it has tab completion, and if I type ROS-spec depends, it's one, and if I press tab, there are 237 packages included in a ROS system. Not going to dive into all of those, but there are a lot of packages standard in this container. And that's also the benefit of ROS. Maybe I can dive a little bit, do a little tangent and dive into it. So if you install ROS or you use our ROS Docker, pneumatic Docker container, there are a lot of interesting and handy libraries available out of the box. If you see here, some laser libraries, image libraries, joint state for controlling an arm. We have a robot called TurtleBot version 3, so it has a lot of packages for that. Let me see some other things that are maybe PCL conversions, so point cloud things, stuff like that. So all those things are already included in ROS. So you don't have to develop or search for those things. Just out of the box, you have vast amount of cool and useful packages. All right. So again, a list of all dependencies of the packages. Package.xml, I'll just open it in Vim. All right, and let's create a publisher. So there's a directory called src. So let's dive into the src directory. And of course, I'm not going to let you type all the code. We have some examples. So you can copy just the examples, and they're under, if you just type cp for copy. Then you can press tilde and example code. I think 02 is ROS, 01 for CLI. I'll keep the command on screen before I execute. And let's copy the publisher to point to this directory. So cp tilde example code 02 ROS 01 CLI and publisher space and point is the current directory. So you just copy the code to this directory. I know it's a lot of typing, but this is less typing than let you completely write the Python code. Look at all. first of all, let's look at the code. It's just a very simple example publisher. Just imports an operating system OS library from Python and the ROS/Py, the ROS Python bindings. And from the standard messages, it imports string. We're going to play around with strings. So if the script starts, just the standard Python way to say if the script starts, like the int main of a C++ program, we have a publisher name. So that's the name of the node. Each node needs to have a unique name in a ROS graph or ROS system. So what I did was just test publisher string and added just the process ID of the Linux that the process gets from the Linux kernel, and that's always unique. So the name of the node will be dash publisher followed by the random, not so random, process ID. And then the topic name is just test topic. What we are going to do is initialize our node. Just say to the ROS master, hey, we have a new node with this name called test publisher and then the number, and it's not anonymous. And then we start a ROS publisher just by typing or executing ROS/Py.publisher. We have to supply the topic name, the type, in this case string, and a queue size. In this example, we have a small queue, just a example, so queue size of 1. And that's the only code you need to initialize a node. So 2 lines, initialize a node and start a publisher. Of course, we want to publish. So I created a while true, just start publishing. Added raw input, that's just it prints on the command line and you can just input enter and just wait. That's the only thing it does. So you don't have an endless loop just spawning your topic full of data. And then we'll just create a string and send it to the publisher. And in the meantime, log it a little bit. So let's execute it. And if you want to execute it, there are a few ways you can do it, but the cleanest way is typing ROS run. Oh, ROS run. The name of our package, that's first package. And then the name of our node, which is publisher.py. It will print out, ready to send data. And if I press enter, it will just send data, data 1, data 2, data 3. And that's just a counter that will just up to 1, up to 1. It's just very simple. It just sends a simple string, just an example. All right. So that's the publisher. Of course, we want to see the other side. So the subscriber, that's this one. Let's open another terminal, attach bash, go into our workspace. Again, first package, src. And of course, we see here the publisher, but I also have a subscriber in the example code. So in the same directory where the publisher was, there's also a subscriber. Subscriber. And let's copy it to this directory. I'll wait a little bit so you can follow. Yeah.
Ja, ik ben wel op zoek naar de example code.
als je de URL aan de post komt, en dan in ROS Big Data goed gedaan, dan heb je daar examples staan. Nou, examples. Daar. Zo het gezegd. Dus je Ctrl-N. Voilà. Ik denk dat je terug overgaat. En dat is nu dan project. Ctrl-N. Nee, nou dat moest ook.
Kunnen we eens laten zien hoe die andere package juist komt?
Ja, ik kan het ons zeggen.
Of
ja,
Rossum. Maar is er iets anders
de extensie.
Publisher.
Daarom dat ik erin aan het gewend om dat te doen.
Ik denk iets denken. Ja. Het is dat tussen. Ja. Dan kun je op enter duwen, dan begint het te sturen. Ja, die gaat geen. Ja, het is maar een eenvoudig voorbeeldje. En dan kun je een volgende term on the client, de subscriber runnen. So let's start and this ROS run. First package. Oh, no idea why I typed forward on this. First package subscriber. It doesn't print anything, but if I send data, it receives data. It's very simple, just to get to the basic things. So that's how code, a string is sent and received. And the code for the subscriber is pretty similar and very easy. Also include the same libraries. There's a callback function to receive the data. And in the main method, or construct in Python, I also created a unique name for the node, named test subscriber, followed by the process ID, the same topic name, test topic. We initialize the node same way, the name and not anonymous. And to subscribe to a topic, you just type ROS by subscriber, the topic name, the string name, and a callback function. And each time a data is pushed onto the topic, the callback function will be executed, and you can receive the data. So in a few lines, you can receive data from a topic. Super easy, quick way. And in C++ is similar. Of course, in C++ you have to compile it and then run it. But the names are almost the same. And of course, you have a bit more work with your types in C++. All right. So to run it and build it and stuff like that, of course, we already had that ROS core running. So ROS core has to run. And then other terminals, you can start a publisher, install a subscriber, send data between them. Of course, we can also open a new terminal. Start RQT graph and see the graph. So we have two 2 nodes currently with a test topic, and the publisher has a process ID of 2088 and test price 2200. It's very simple. If you have a complex system, of course, then there are a lot of nodes. The next, I'm just going to show you. You don't have to type it on your own. It's the same concept, the same way, just copy code and execute it. But it's the service. It's a bit more complicated. So I'll let you do it now by hand. It's error prone, and there are a few, 2 more dependencies that are needed to supply if you create a package. So if you want to create a service, like you can create a package, you call it whatever you want. In this case, it's just first service. And apart from the standard messages and ROS², you also have to add message generation and message runtime. And that's to create the service and to interact and to be able to let another node interact with the service. It works with an SRV file, which is a service file. It's all in the example code, so you can do it, but to speed up a little bit and explain it just by this presentation. So if you look at the SRV file in this case, you have to supply 2 values, A and B, and the reaction will be 1 value. And in this case, we're going to just create a service that will just add A and B and return the sum. Nothing fancy, but just to show you how it works. So it's just a very simple file format. You just before the 3 dashes, you just add whatever messages or whatever types are needed to be submitted in the request, and after the dashes, what type will be returned. And this can be in this form, very easy. So there's also, of course, a command to show you in ROS the service. And then the less fun part is you have to edit the CMake list file. Those of you who work with C++ probably already know CMake and know CMake list files. So this is the part where our students most of the time make small mistakes and then it doesn't work. So that's why I just go over the slides. If you want to create a service, there's a block add service files in the CMake list file of your package. You have to add your service, and in generated messages, you have to add the dependencies. Don't forget the S, something what my students miss, and then it doesn't work. So it's a bit error prone, this part. You can just copy the service file if you want to. But so create a service, then you have to build it. And building is this is the command to build it. It's catkin_make -- pkg first service, and you have to execute it in the topmost src directory. So that's.
You can also execute catkin_make without the package name.
Yeah.
And then it just makes everything.
Yeah, but if you have a lot of packages in your workspace, that can take some time. So most times, if you have everything built and you're just changing stuff in one package and you don't want to rebuild everything, just supply it. So that's the directory where you want to execute it. But let's just keep to the slides. Keep to the time constraints. All right, so that will just generate everything. And this is the code for the service. It's a bit more than a publisher, of course. So you have to import your SRV file. So the file that defines how the service operates. I import ROS². I have two functions defined here. So let's just see which one is called first. Add to instance server, that's this one. This will initialize the node and create a service. And create a service, just rospy.service. The name of the service, it's like the name of the topic. Now it's a service. What format it has, so the SRV file from first service, it was add to int, what it was called, and the callback, or the function that's used when the service is called. And then you spin your node up, and then this function will be called when a request is received. And here it's very simple. I just print something that I will receive two values, and I'm going to return the sum of the two values. And return is a bit strange maybe, but that's auto-generated. So it's add to int, that's the name of your service file, and add it with the word response. And that's how a service is defined. On the other side, so we are creating it, importing it, and then you can run it. On the other side, the client side, if you want to use a service, it's a standard node. I ask for just some command line data, so you can execute it with A and B, and that will call the service with those two values you supply from the command line. I have an example in a few slides. So if you want to use a service, you have to use a service proxy. That's just a way to call a service. You have to supply the name of the service, how the service operates, so the SRV file, and then just call it like a function, and you get the result. It's like proxies in C++ and in other languages. It's the same concept, just in ROS. So if you run it in the service, so you start your ROS core, you start your service, and in a third terminal, you can add two parameters or two arguments to your client, and that will just send a request for 1 + 1. You receive 2 and stuff like that. It's just very similar to publish subscribe, just this is more for things that take a lot of time, a lot of calculations, and just call a service, it calculates stuff, and then it will receive, your program, your client will receive the data. Right. So those are the main constructs of Python, actually. So publish, subscribe, that's the main way. Just if you have a lot of throughput, videos, laser, stuff like that. And for bigger things, less common use as a service. All right. And the last slides I have are just a lot of extra information. And then we'll dive into computer vision. Time flies. So just extra information. So there's a lot of documentation of ROS. Also has a lot of tutorials. The service subscribe and the publish subscribe and the service and client are just examples from those tutorials. Yeah, it's complete ROS course for a few days. So that's everything from starting from beginner level, as well as intermediate and advanced things. So it's really good. But that's too much for today, of course. It's in Python and in C++, depending on what you want to use. Both are there. Gazebo is the standard simulator ROS used, and I'll maybe show you one of the summer of all for all. One of the student projects for summer, if they fail my course, they have to do the summer course or the summer project. This Gazebo is just a simulator, and we have a robot in here, which is just, we don't have him here currently, Turtlebot. version 3 with a LiDAR on it and a depth camera. So we're going to play around with it later. And my students have to just race on the track and avoid and use computer vision in this case, and avoid certain places and do things on the circles. So that's what we do with that. So that's another thing I can show you is this might take a while. It's called a roll. It's a track full of boxes, so our students have to avoid the cardboard boxes and cinder blocks. It's currently downloading a lot of models, so it will take some time. So I'm going to the other slides. If my splash screen will go away. Go away. Oh. Yeah. Yeah, I'm going for squid. I'm going to show you later on because still. All right. Voilà. So Turtlebot has some configurations with a LiDAR or with of things. I also have in the ROS container a few commands. Kill all Gazebo, kill all ROS. Sometimes your system goes haywire and does a lot of silly things, like my system just did. And then you can just execute kill all Gazebo, kill all ROS. That's something we provided in the container. It's not something standard from ROS, but feel free to use it wherever you want. It just kills everything. There's also a nice environment or virtual world for the Turtlebot. But we'll show it later on. We're going to do a slam in this environment, just some pillars, and you can run around with the Turtlebot. That's a configuration my students have to use with the depth camera and the LiDAR together. There's also a cool program called ROS. We're going to try it again, and hopefully it won't crash again. Voila. So this is the track my students need to run through and avoid the boxes. Reason I want to show you this is I open ROS. It's a cool program where you can add visualizations of certain topics. For example, our RGB camera has. That's okay. So this is the video feed of the camera, just straight from the robot. If I take the robot and just move it, you see the move it then. Am I not playing it? Yes, I'm playing it. Cool. That was scaling, moving it. You see, of course, camera moves. You can run around and do stuff with it. You can also visualize the LiDAR and stuff like that. So it's very handy to visualize everything and inspect your topics and see your environment through that program. So ROS, super handy. So depth camera, everything you can visualize in ROS. There's also a version with Pi on it. That's not really interesting now, with a Pi camera. Another virtual environment we use is Unity. Maybe not so interesting since last week, since they are starting to ask quite a lot of money for each installment. 20 cents, I guess it was, for each installment. So, but until last week, it's a very good environment. It's a game engine actually, but they have a complete team working on ROS and ROS² interaction. So we use it in some courses and some projects to visualize the robots. It's just nicer to see, actually. That's the reason why we use it. But they have a complete team working on it to improve it for ROS. So they have a complete nav2 SLAM examples for ROS². But we're going to see other examples today. Another one from Microsoft is AirSim. We use it with UAVs. It's a really great system, but especially for, the name says it already, for air simulation to do those kinds of things. Also, of course, ROS compatible. Another one, but more for cars, actually, for automotive, is Webots. You can also do other robots in it, but as far as I know, it's mostly used for automotive real-time stuff, advanced automotive things. And last one is VRAP, or Coppelia Sim, how it's called today. It's used for like some KUKA robots are simulated in that system. But actually, most of the time, Gazebo was used in the ROS world. That's the standard version, the standard simulator, but others can also be used, of course. It's also possible to record and play back all the messages in your ROS framework, or ROS graph. So what we do, and what a lot of other groups do, is just do a test run with a robot, capture all the messages that are sent, and then you have a big file, and you can just replay it and just test different algorithms on it without running the real robot again, but having all the standard messages and everything that happens in a large bag, a large file. So super handy to do. There are some limitations, of course. If you replay a ROS bag, it's like operating a real robot. Sometimes you have timing differences, and it's not perfect. You don't have a perfect rerun every time, because sometimes, yeah, your system calculations are take a bit more time, and then you have a little bit of different run with your robot, but that's like in real life. So there's also a command called ROS-WTF. If something goes wrong, you can use it. It's something actually I never use, ROS-WTF, but it exists. RES is a lot of cool information on services and parameters, all in the documentation. RQT console to look at everything in your ROS graph. ROS launch is if you want to start a lot of nodes. That's actually what I did with my ROML command, or Summer for All. That was just a launch file in the backend and just starts multiple nodes. So that's super handy. A lot of information on messages and services are also in the tutorials. There's a coding style for Python, for C++, if you want to follow it and open source your project and share it with the community. So read into it. Also some interesting books. This one is the ROS robot programming book for the Turbo 3, and an open ARM, open manipulator ARM. It's for a older version of ROS, but the basic instruction and concepts, it's just free to use. So feel free to dive into it, and it's for getting to know the basics. It's good. Another one is a gentle introduction to ROS. You can buy it, but the digital copy is just free. So we added the link, so you can just download it and use it that way. It's using C++ to introduce you gently into the world of ROS. All right, so that's everything in a nutshell. A bit sped up because of time constraints. On ROS, questions. I know it's a lot of information. No. All right, it's time for another break, or just dive into computer vision. Mini break. All right, mini break. And maybe I'll stop the recording. Everything is one video now.
Don't forget to start.
Yeah.